Okay, good afternoon. Now we have today and next week, and we are almost at the end of the course. And these 2 weeks is really a big opportunity for you to gain a lot from this course. And of course, to get an advantage for the final. We are talking about eigenvalues and eigenvectors. We said that eigenvalues comes from a problem like this. For example, this is an example of where eigenvalue and eigenvector comes up. So you have a system of linear differential equations, system of first order linear differential equations with given initial condition, and you would like to find a solution for this. We said that we look for a solution like this. Okay, these are vectors. We say that can we find a solution like e to the lambda t c? And when we substitute it here, we said what is x dot here? I'm just repeating very quickly so that what is the derivative of lambda e to the lambda t c? And you substitute here what we have, lambda e to the lambda t c is equal to a e to the lambda t and c. So e to the lambda t is always greater than 0. Therefore, you need to just solve a minus lambda I times c should be equal to 0. Okay? And this problem, when we look at this, when can we find a solution for this? When does it have a solution? Of course, if c is equal to 0, that would satisfy this, isn't it? So what is wrong with that? What's wrong with c equal to 0 as a solution? Not satisfy the initial condition. So we call that the trivial solution. So yes, it is a solution of the differential equation. Therefore, it's a solution of this, but you cannot satisfy the initial condition with it. Therefore, we are looking for non-trivial solution. So meaning we would like to have c different from 0, right? 0 vector. So we are not writing these vectors most of the time because from the context it's clear it's a vector. Okay? So when c is different from 0 and this is satisfied, then what do we need? When does such a, if c is different from 0 and a minus lambda I times c is equal to 0, what does this tell you? So remember, when you have ax equal to 0, what is x? X is in the null space of A, right? So for a matrix to have a non-zero vector in its null space, what do you need for that matrix? For a square matrix, it has to be singular. Yes, good. So this, such a system of course, this is a, in fact, this is a nonlinear system, isn't it? You have unknowns are lambda and c, and they are multiplied together. Therefore, it looks difficult. But using what we learned from subspaces of matrices, such an equation would have a solution if this has a solution, has a non-zero, or let's say non-trivial solution, only if A minus lambda I is singular, is a singular matrix. Okay? What is a singular matrix again? Let's go back to the basics. What's a singular matrix? Excuse me? It's columns or rows, meaning that matrix has a dependent column or row, at least one pair of them, right? So in terms of Gaussian elimination and the pivots, what does that mean? It means it has 1, 1, 0 pivot, right? Okay, good. Now we learned about determinants, so this was equivalent to having determinant of the matrix is equal to 0, right? So if it's a singular matrix and A minus lambda I, so this is how different concepts are now connected together, right? It's singular if determinant of A minus lambda I is equal to 0. So this is very nice. We decoupled the problem now. So to solve such a problem, we first determine the lambdas that will make this matrix singular. Then for those lambdas, what are you going to have? A minus lambda I will be a singular matrix. Then we look for the null space of that singular matrix. So we find the vectors in the null space of the singular matrix. Those vectors are what? Eigenvectors. Very good. Very nice. Okay. Of course, whereas I gave you another example on this, I'm not going to do it again. In difference equation again, right? In difference equation also, you face an eigenvalue problem. Whereas in many, many places, thousands and millions of places, eigenvalue, eigenvector problem comes up. Okay? Okay. So let me give you an example. Let's say A is 2, 1, 0, 3. Okay? So I'd like to find the eigenvalues of this. So find the eigenvalues and the corresponding eigenvectors. Now, I did not write a differential equation here. It doesn't have to be a differential equation, right? So this differential equation is just one way where eigenvalue problem would come up. So it could come up from many other physical problems. Therefore, we do not talk about this unless we come back to it. Okay? We will come back to it in stability after a while. But in general, we give you a matrix, a square matrix, right? For eigenvalues and eigenvectors are defined for square matrices. So we ask you to find eigenvalues and eigenvectors and other properties of it. Okay, so what should I do? Determinant of this should be equal to 0, right? So A is this 2, 0, 1, 3 minus lambda 1, 0, 0, 1. So that is equal to 2 minus lambda, 0, 1, 3 minus lambda, right? This determinant of this should be we should be careful with our language. Okay? So what is the determinant of a triangular matrix? Multiplication of the diagonal elements. Very good. So that's equal to 2 minus lambda, 3 minus lambda. That should be equal to 0. Okay? So for which lambdas this is equal to 0? Lambda 1 is equal to 2, and lambda 2 is equal to 3. So we have two eigenvalues. So it is a 2 by 2 matrix. You have two eigenvalues. If it is 5 by 5, how many eigenvalues will you have? 5 eigenvalues. Of course, provided you also allow complex solutions, complex roots for the eigenvalues, right? So complex or real, in total you will have, for an n by n matrix, you will have n eigenvalues. Some of them could be repeated. For example, if I have a matrix, identity matrix, 1, 0, 0, 1, what are the eigenvalues of this? What are the eigenvalues? So A minus lambda I is 1, 0, 0, 1 minus lambda times 1, 0, 0, 1. What is that equal to? 1 minus lambda, 0, 0, 1 minus lambda. So determinant of A minus lambda I is equal to, what is the determinant of that? 1 minus lambda squared, right? So set is equal to 0. So you have lambda 1 is equal to 1, lambda 2 is equal to 1. Okay? Let's keep this here. Okay, let me first find the eigenvectors of this. What are the eigenvectors of this? Remember, we are looking for a x is equal to lambda x, right? This is how we started, right? A minus lambda I. So you are looking for, this means AC. So when you have A minus lambda x times lambda I times C equal to 0 means, just open this up, this is AC is equal to AC minus lambda C is equal to 0. In other words, this means AC is equal to lambda C, right? So AX is equal to lambda X. So this lambda is eigenvalue and X is eigenvector. When A is an identity, for what X, if you multiply A with that X, you will get it back, a multiple of it back. For what X? Huh? All, right? For identity matrix, whatever you multiply it with, you will get it back. You will get it exactly back, right? Not multiplied with any number. So what are the eigenvalues? 1. Even this is n by n identity matrix, all eigenvalues are 1, and every vector is an eigenvector, right? So the entire, it maps Rn into itself, and it's just by itself, okay? So it doesn't do any rotation or anything else. So therefore, I didn't need to even calculate this. So you have to know what eigenvalue is. When I give you, for example, in the exam, this is identity. If you do this, I will be upset. I will say he didn't understand. He just memorized the math and he's just mimicking it without understanding what he is doing or she is doing, right? So you should understand that when I give you an identity matrix, you just multiply identity times x. This is equal to x. Therefore, so lambda here is 1. And this is just, any x is an eigenvector here. Okay? But can we say the same thing for this one? No. So we have to compute. So for this matrix, 2, 0, what was it? 1, 3. So we found that lambda 1 is equal to 2. Lambda 2 is equal to 3. So how do I now get my eigenvectors? Who wants to tell me from the back rows? How do I get the eigenvectors? So A minus lambda 1I, right? So this matrix should be what? this should be singular, right? We picked lambda 1 and lambda 2 so that determinant of this is equal to 0. That's how we computed lambda 1 and lambda 2. That was the whole thing, right? So this is going to be 2 minus lambda 1, 1, 0, 3 minus lambda 1. So that is equal to 0, 0, 1, and 1. So I need to find the vectors that span the null space of this, right? This is how we look at it. So find the null space. So what is that? 0, 0, x1, x2, 0, 0, 1, 1, x1, x2 should be equal to 0, 0. Okay. What does the first equation give me? The first one is 0. Second one tells me that x1 plus x2 should be equal to 0. x1 should be equal to minus x2. Okay, so x is 1 minus 1. Right? Meaning if you multiply this vector with this, as you see, the first row will give you 0, second row will give you 0. So it is in the null space. So this x is, so lambda 1 equal to 2, and x is equal to 1 minus 1 is an eigenvalue eigenvector pair, meaning a times x is equal to lambda times x. Let's verify that. So it is 2, 0, 1, 3 times 1 minus 1 should be equal to 2 times 1 minus 1. Is this true? Okay, let's multiply the first row into this. What do you get? 2. So that's true. This 1 minus 3, so it is minus 2. Yes, it is minus 2, so it's checked. Right? Oh, it's killed. Okay. Okay. So let's do the other one in the small place. So a minus lambda 2I. So what is that? 2 minus lambda 2, 0, 1. This 3 minus lambda 2. So that is equal to 2 minus 3, which is minus 1. 0, 1, 0, right? So this is again, we need to find null space of this. So it is a different one, right? So what is the nulls? Find a basis, a set of bases. Let's write it, set of basis vectors for the null space. This is the exact terminology, space of A minus lambda 2I. Okay, so minus 1, 0, 1, 0, x1, x2 should be equal to 0, 0. What does the first one give you? Minus x1 is 0. The other one? So x1 is 0. x2? No condition. So therefore, what is the basis for the null space? 0 and 1. Okay? So we should have then A times x should be equal to 3 times x. Is it true? Let's see. 2, 0, 1, 3 times 0, 1 should give us 3 times 0, 1. Is this true? So the first one gives us 0, checks. Second one gives us 3 and 3. Yes. So eigenvalue and eigenvector, we have them. Good. Okay. One example I gave you last time, I want to As a matter of fact, I will give even a simpler example. So we just talked about eigenvalues and eigenvectors of this, and we said we have two eigenvalues and two eigenvectors. Just any x, right? Any x in R2 is an eigenvector for this example, right? Not in general. So nobody tell me that, sir, you wrote in the blackboard that any x in R2 is an eigenvector. Not for this example, yes. You just multiply with any x with this, you get it back. And eigenvalue is 1. So I will give you a slightly modified example. 1, 1, 0, 1. Okay, what are the eigenvalues of this? Again, lambda 1 is equal to 1. Lambda 2 is equal to 1. Why is that? A1 minus lambda I determinant is equal to 1 minus lambda 0, 1, 1 minus lambda determinant, okay, equal to 0. So this also gives you, again, the diagonal. You just multiply the diagonal elements, so you have 1 minus lambda square is equal to 0. Therefore, you have the same thing. But let's talk about now eigenvectors, okay? So A1 minus lambda 1i is equal to what? 1 minus 1, 1, 0, 1 minus 1. So what is that? 0, 1, 0, 0. Okay? Let's find the null space of this. Can we say that any x satisfies that? Because before this was becoming 0, right? So what are we going to have now? 0, 1, 0, 0 times x1, x2 is equal to 0, 0. So what does this tell you? x1 is equal to 0, right, from the first one. And the other one, no condition. Nothing about x2. So what is an eigenvector? 0 and 1. Okay? If you multiply, let's check it. A1 times x should be equal to 1 times x, right? So meaning 1, 1, 0, 1 times 0, 1 should be equal to 1 times 0, 1. Any question?
It is 1, 0.
Excuse me?
It is 1, 0. No,
It's not x1, x2,
x2, 0, yes. x2, 0, yes. Yes. So I would find it out now, right? So when I check this, I would find, okay. So is this satisfied? Okay? So 1 is equal to 1. 0 is equal to 0. So therefore it's checked. Well, how about, now I have two eigenvalues. Do I have a second eigenvector? Can I find, what is the dimension of the null space here? What is the rank of this matrix? How many pivots do we have? Non-zero pivots. 1. What's the dimension? 2. So therefore, column space has dimension 1, and null space has dimension n minus r. So it is 1 again. So there is no other linearly independent vector that belongs to the null space. Therefore, unfortunately, or whatever, this is the truth. You do not always have n linearly independent eigenvectors. When you have that problem? When can you have that problem? Okay? Let me now tell you some basic truths. Okay? Everybody note this. If you have n distinct eigenvalues, so you have lambda 1, lambda 2, lambda n, and none of these two are equal. They are all different from each other, okay? Then you have n linearly independent eigenvector. So every eigenvalue has an eigenvector corresponding to that eigenvalue. It's guaranteed. if you have multiplicity of some eigenvalues, so if some eigenvalues like here, you have two matrices here. This has lambda equal to 1 is a double eigenvalue here, and here is also double eigenvalue. In this case, you have two linearly independent eigenvectors, but in this case, you don't have it. So, if the eigenvalues are not distinct means none of the two are equal, okay? Then you might have or you might not have linearly independent eigenvectors, okay? As this example shows. Maybe I will prove that if I have any time left, I will go over the proof. Why is this true, okay? But I want to now continue a little bit more and go further. This was like a repetition of what we did last class. So about 25 minutes passed. Okay. We have to count every minute now because there is limited time left. Okay. Now, last week also I gave you this example. Okay. Let's talk about this matrix. Okay, we would like to find the eigenvalues and the eigenvectors. Okay? So, same question. Find the eigenvalues. Find the eigenvalues. And the corresponding okay. Find the eigenvalues and the corresponding eigenvectors. Okay, so what we know the drill, right? A minus lambda I is equal to 0, 1, minus 1, 0, minus lambda times 1, 0, 0, 1. That's equal to minus lambda, minus lambda, minus lambda, minus 1, and 1, right? So determinant of A minus lambda I then is equal to determinant of minus lambda 1, minus 1, minus lambda. So that's equal to what? Lambda square minus this times that. So plus 1. So we should set this equal to 0. So what are the eigenvalues? So lambda square plus 1 should be equal to 0. That means lambda square should be equal to minus 1. Okay? So square of what is minus 1? Not a real number, right? It is complex unit. So lambda 1, 2 is equal to plus or minus j. Of course, I love to use I, and I am a mathematician. But in electrical engineering, computer engineering, and telecommunications, we always use J because we use I for current. Okay, current is the basic thing we deal with, voltage and current, right? So whole electrical engineering is about that. So we use, in electrical engineering, we use J. So this has complex eigenvalues and eigenvector. What I want to do now is give you a basic understanding of complex numbers. So these complex numbers and theory of complex functions and complex analysis is an extremely powerful tool of mathematics. I recommend that you learn it. There is a course being offered, I think, in the 3rd semester or something. Those of you who love mathematics and who would like to really go in the theoretical direction, they should certainly take it. But let me give you a basic understanding of what is a complex number, okay? Because the course we will use complex numbers and related things, so I want to make sure everybody in my class has a basic common understanding of what we mean by terminology. So complex numbers. Again, like it is there, when I have an equation like this, and I want to find the solution of this, there is no real number that will satisfy that, because square of a number is always positive. Even for a negative number, if you take square, if you multiply it by itself, you will get a positive number. Therefore, having a number that is square of it is negative requires us to extend the real number system into something else, okay? And this was done several hundred years ago, and we introduced the complex numbers. So we talk about complex numbers, we call them Z, or in electrical engineering, we call them S. When we talk about Laplace transform, we call them Z when we talk about Z transform. So let's say Z, it has a real part, and it has imaginary part, okay? J omega, let's say. So these are now real numbers. So you talk about a plane. So in real number system, we talk about a line. It has a 0, and it's 1, 2, it goes all the way till infinity, and -1, -2, etc. When we talk about complex numbers, we talk about a plane. It's like a two-dimensional vector space. It has a real part, and it has an imaginary part. Okay, when we talk about complex numbers, let's say r plus j omega, that means this is real part is r, and imaginary part is j omega. So you can look at this like a vector. Okay? This is called the Cartesian representation of the complex numbers. Okay? We can also talk about polar representation of them. We can call this angle as theta. Okay? What is this equal to? What is the length here? Length of this vector? This is a triangle, right? This is r and this is omega. So what is this? So this is square root of r square plus omega square. Okay? So in terms of real and complex part, how can we represent them in terms of, this is, okay, I should not call this r, right? R is this. So for real, I called it r. So let me call this A and B. I'm sorry, okay? A and B. Okay? So A square plus B square. It doesn't matter which name you call them, right? It's not an error. It's just, it's better that we just keep this for R, okay? So A in terms of R and theta, how can I represent that? So this is a right triangle, right? So you have hypotenuse is R. You have theta here. What is this equal to? R times cosine theta. And what is B? R times sine theta. So if you write again Z is equal to A plus JB, you have R cosine theta plus J R sine theta. In other words, R cosine theta plus J sine theta. So this is representation of complex numbers in Cartesian coordinates and in polar coordinates. Any question about this? Who has not seen complex numbers before? Please raise your hand. Who has seen complex numbers? Did you see it this year? Where did you see it? High school, they teach you complex numbers? Everybody learned complex numbers? Which high school you were in?
Taking the class at second year,
Okay, you are taking complex number theory. Okay. Okay, so you learned this. Good. That means I have to spend even less time on it, so we can go back to matrices soon. Okay, so one way to look at this is this. So when you have z equal to a plus jb, complex conjugate of z is called z bar. So what is this equal to? So you just replace j by minus j. That's all. It might be a very complicated expression. So to find the complex conjugate, wherever you see a j, just replace it by minus j, okay? It could be very complicated, so you don't have to first bring it in this form and replace j. You can do it at any moment. You can just replace j by minus j, so this is complex conjugate. So what is z times z bar? That's equal to a plus jb, right? A minus jb. So this is equal to, so this is a times a minus a times j, a times b, and plus j, b times a, and minus j square, b square. So this will cancel. What is j square? Minus 1. With this minus it becomes plus, so therefore it is a square plus b square. Therefore, z times z bar is equal to a square plus b square, which is, we call this absolute value square of z. Okay? Who has not seen Taylor series? Anybody that has not seen Taylor series? Taylor series, you did not see it? This semester they did not teach it to you? You didn't. So what are you learning in Calculus 1, in Mathematics 1 so far? What is the current topic? What? You are learning integrals before you learn Taylor series? That's very interesting. So second semester, so they messed it up. So the curriculum is upside down. Anyway, so I will just give you again 5 minutes on Taylor series. Let's talk about calculating function. If I tell you, for example, my function is x squared plus 2, calculating this for a given value, let's say 1.3, it's very easy, isn't it? You can just say 1.3 square plus 2, right? You just take square of it and add it, you get it. For any polynomial, if I give you a polynomial px, the a n x to the n, etc., a1x plus a0, again, you can very easily calculate it by using like multiplication, addition, and that's it, and subtraction. There is no need even for division, right? So you can always obtain a value of this function using your four elementary operations. But when it comes to a function like this, sine x, cosine x, e to the x, logarithm x, anything other than polynomial, you are in trouble, right? So we would like to see how we could compute the values of these functions other than polynomials. So in that case, what we do is the following. We say that, okay, of course, everyone knows about derivatives. Let's say we are able to compute the derivative of a function at a given point. So how can I find an approximation of that function around that point? Okay? Let's say this is your real axis. Okay? This is 0. And around this point, you know f, let's call this x0. You know x0, f prime x0, f double prime x0. You know all of these, right? And prime x0. You are able to compute all these. How can I find the polynomial approximation of my function that's not a polynomial, or it could be a polynomial as well, around that point? where I know the function's value and its derivatives. And I want to use that to compute the value here. Okay? Using that polynomial, I want to obtain an approximate value of my function using that approximation. Okay? A nice way of looking at it is this. I say, I am given a function x, and I would like to find an approximation of this in terms of polynomial. Meaning, I want to find an a0, and I want to find an a1 x minus x0, a2 x minus x0 square, okay? an x minus x0 to the power n. I want to continue like this. How can I determine a0, a1, a2, an so that my function is equal to this polynomial I will get? Hopefully it can be a finite polynomial or infinite polynomial. Okay? Is a close approximation of my function, like e to the x or cosine x or sine x or logarithm x. So what is a logical way of finding it? Of course, I cannot find a polynomial that is equal to my function for every value of x, isn't it? Then that function itself would be a polynomial. So we are talking about approximating a function in a neighborhood where you know the function itself. Okay? So what would be a logical way of looking at it? Two functions, okay, there are degrees of being close to each other, right? If two functions have the same value at some point, that's a plus. You say, okay, good. At one point, this function and my polynomial, they have the same value. What would be even better? If their derivatives are also equal, it's even better, isn't it? Okay, how about if their second derivatives are also equal? Third derivatives are equal. Nth derivatives are equal. Wouldn't that be even better and better and better? Right? So the more matching you have between the two functions, that their values are equal at that point, their derivative, first derivative, second derivative, nth derivatives are equal, that's very nice. So you expect that that function and those polynomials are resembling each other quite nicely. Of course, there is a theory behind this. In calculus, they will teach that to you. So how close is it? What is an upper bound for the error and things like this? I'm not going to talk about, but I will give you, it's so nice and easy. So if I want to say that I want function, okay, and the right-hand side and left-hand side to be equal. So what is fx0? If I substitute x equal to x0, what do I get here? What happens to this? Everything else is 0, right? So this is a0. Okay, let me take the derivative of this. What is the derivative of this? F prime x is equal to, so this is constant, right? Plus a1 plus, what is this? 2 times a2 x minus x0 plus 3 times a3 x minus x0 square and n times an x minus x0 to the n minus 1, etc. So now I want to have f prime x0 equal to the polynomial itself. So if I substitute this, what do I have here? Everything else is 0 except a1. How about I take second derivative? You now learn the game, right? If I take a second derivative of this, what do you have? 2a2, no, a1 gone, right? This is constant now. 2a2, then this is 3 times 2 times a3. What is that? X minus x0. You continue n times n minus 1 an x minus x0 to the n minus 2. So if I want to match also the second derivatives, what do I have here? F double prime x0 is, what are these? These are all 0, right? So a2 is 1/2 f prime x0. This is A1, A0, right? So if you continue like this, what are you going to have? If let's say I want to match zeroth derivative, first derivative, second derivative, nth derivative, what is going to be my nth coefficient? You see here? What will be this? If I take one more derivative, what am I going to have here? N minus 1, then n minus 2, n minus 3, n minus 4. So n factorial, right? So I will take nth derivative and substitute x equal to x0. Then I will have everything else will be 0. And I will have f nth derivative at x0 is equal to n factorial times an. Meaning an is equal to nth derivative of x0 divided by n factorial. Okay? This is the beauty of mathematics, isn't it? If I stop at nth term, I can say, okay, this needs explanation, and it needs upper bound, is equal to f0, fx0 plus f prime x0, x minus x0, f double prime x0, x minus x0 square over 2 factorial, all the way nth derivative of f calculated x0 divided by n factorial x minus x0 to the n. Okay? And I stopped here. I continue all the way. Okay? Now, if you do this for e to the x, what is derivative of e to the x? Any derivative is itself, right? So what is just any derivative of e to the x nth derivative calculated at x equal to 0? What is that? It's 1, right? So therefore, e to the x is 1 plus, and x0 is 0 here, x plus x squared over 2 factorial x to the n over n factorial. Okay? This is e to the x. And it turns out that this converges for any x. Okay? Meaning when n goes to infinity, this is an equality. Okay? So if you take infinitely many terms in this polynomial, you always have the exact value of this. So you use this, for example, to compute this. Now, why did I tell you about this? Okay. There is very nice property in complex numbers. So this is true for all x less than infinity. Meaning, for any finite x, this is valid. This is not true for every Taylor series, but for this case, it is true. Okay. This absolute value, what we do is that we replace this with e to the z. Okay? So this is a generalization of the e to the x into the complex domain. Since this is valid for all x's, so and we are talking about this in the complex axis, in the real axis, we say that why not talk about this? Okay? So we are talking about this e to the x on this axis. Instead of that, why don't you talk about it on regions? Okay? So therefore, this is. Now I want to do something special here. Okay? Replace z equal to I theta. Okay? When you say z equal to I theta, what do you have? 1 plus, and this 2 factorial, right? So let's compute this. So this is 1, this is real, this is imaginary. What is this? I theta square is what? I square minus 1. Theta is theta square, right? So minus theta square over 2 factorial. This I times I is minus 1. If you multiply with I again, what do you get? Minus I. So this is minus I. Then what is this going to be? I square is 1. So this theta to the... So what you will have is the following. I am not going to ask you a question about this, so don't worry. But I just wanted to, those of you who wonder about what is behind this, I just want to spend 15, 20 minutes on this so that it has a complete picture on the blackboard. Okay, so this, let me take the real parts. So e to the I theta is equal to 1 minus plus minus all the way, right? Plus this is the real part. In the imaginary part, what do you have? I wrote I, okay? I cannot help it. I get it right, I. Okay, I times, what is that? This theta. And this is minus 1 to the n one over, so for n equal to 1, this is minus 1 to 1. Okay, so for n equal to 1, this is theta over 1. Yes, this is 1. This is, again, if we were to do it, this is the Taylor series of what? Cosine theta. Okay? And this is the Taylor series of sine theta. So therefore, e to the I theta is equal to cosine theta plus I sine theta. Who understood this? Good. Quite a number of people. Did they tell you this before? So this is a miraculous thing, okay? Of course, cosine 2 pi is equal to what? 1. Cosine 4 pi? 1. So cosine 2k pi is equal to 1. How about sine? This is equal to 0. So therefore, I can always write this e to the I theta is equal to e to the I theta plus 2k pi, right? Why? This is equal to cosine theta plus 2k pi plus I sine theta plus 2k pi. As you see, this is equal to cosine. This is a periodic function, isn't it? It's always with 2 pi period, it will repeat the same values. For example, if I want to compute, let's say, I to the power 5. Okay? So what is I equal to? In terms of, so think of it like this. To obtain I, what should this theta should be equal to? What corresponds to? Think of this. Okay, you have this number. So what is the polar representation of, what is the theta here? pi over 2, right? So it's pi over 2. So I is, so I can write I is equal to e to the I pi over 2, right? Plus 2k pi. It doesn't matter. It will always get the same thing. So if you want to compute the fifth power of I, you just say e to the I pi over 2 plus 2k pi times 5. You just multiply the exponent of it, okay? Of course, this becomes important when you are calculating the roots of it. So let's say I want to calculate square root of I, okay? Then this 2k pi starts mattering, right? So what is this equal to? E to the I pi over 2 plus 2k pi times 1 over 2, because square root of I means to the power 1 over 2, right? So this means, what am I going to have here? E to the I pi over 4 plus k pi. So for k equal to 0, how many roots am I going to have here? For k equal to 0, I will have e to the I power 4 for k equal to 0. For k equal to 1, I will have e to the I pi over 4, okay, plus pi. I go all the way here, right? E to the I pi over 4 plus pi. For k equal to 2, what do I have here? I come back to this one. So it keeps repeating. So it has 2 roots. Square root of I has 2 roots, okay? Now I want to give you one more example and give a break. How about this? I to the power I. Okay? What would this be? Do you wonder what it would be? This is how you do it. So what is I equal to? E to the I pi over 2, right? Plus 2k pi times, so this is power I, right? So you just, we multiply it with this, what do you have? E to the I squared pi over 2. So what is I squared? So this is minus. Is this complex? Is this a complex number? Is this a complex number? No. How many, should I say, roots or powers does it have? How many? For every k, it's a different value, isn't it? Infinitely many. So I to the power I is a real number, and it has infinitely many different and distinct values. Okay? So square root of I has 2 values. 10th root of I would have 10 values. But ith power of I would have infinitely many values. So this complex number domain is like a new world you open into. Okay? It gives you some things you have never seen before. Okay? Let's give a 5 minutes break and we will continue. We'll go back to the matrices. So therefore, when we have a matrix like this, we found out that lambda 1, so lambda square plus 1 is equal to 0. We'll give you the eigenvalues. Therefore, lambda 1 is equal to I, and lambda 2 is equal to minus I. So I will keep writing I, because now we don't have electricity in this course. Therefore, we can use I here. Okay? So therefore, I need to find now I found the eigenvalues, so I need to find eigenvectors, right? So A minus lambda I is 0, 1, minus 1, 0 times I 1, 0, 0, 1. And that's equal to minus I 1, minus 1, and minus I. So what do I need to find now? I need to find the null space, the vectors that span the null space of this singular matrix, right? This is a singular matrix, okay? So therefore, of course, now x1 and x2 can be complex numbers. Now since we started having this complex numbers, we allow the complex numbers into our calculation. So x1 and x2 also could possibly be complex numbers. So this has to be equal to 0, 0. Then what do I have here? The first one tells me minus I times x1 plus x2 is equal to 0. Second one is minus x1 minus I x2 is equal to 0. Okay, so this tells you x1 is equal to minus I x2. So I take x2 equal to 1. I take it as my free variable, right? So x is equal to 1 and minus I. It should also satisfy this, right? If you take x1 is equal to minus I, what do you have here? Minus 1, right? Minus I times minus I makes I square. I square is minus 1. X2 is 1. Therefore, it is 0. Okay? So this is one eigenvector. So it is minus I and 1. So what is the other one? So I will take A minus now lambda 2I. I'm just doing this so that you have some exercise, okay? 0, 1, minus 1, 0 times minus I, 1, 0, 0, 1. So that gives you minus minus I, so this is I, right? And this is 1, and this is minus 1, and this is I. Okay? So what is A minus lambda 2I, the null space of this? What do I have from here? I times x1 plus x2 is equal to 0, and minus x1 plus I x2 is equal to 0. So from here, I would have x1 is equal to I x2, right? So I can have just take x2 equal to 1. Then what do I have here? I have I, right? Are these eigenvectors? Let's check. Okay, let's do verification of it. So Ax equal to lambda x, right? So I have A here is 0, 1, minus 1, 0 times, what was the first one? Minus I and 1. What is this equal to? So multiply. So it is 1, and this is I. Okay? So this should be equal to I times minus I and 1. Is it true? So this is x, right? X, and this is lambda. So this is I times minus I squared. It's 1. And this is I. Is this? Yes, it's I. Okay? It's true. How about the other one? 0, 1, minus 1, 0 times I and 1. This gives you 1 and minus I. This should be equal to minus I times I and 1. Is this true? So this is, so minus I times I squared is plus 1. And this is minus I. So this also checks. So this is lambda, right? And this is the eigenvector. Now I want to, before, oh, this I have to tell you this. I will go back to complex numbers because I wrote it to remind myself. This cosine, this sine alpha plus beta, what is this equal to? You remember that? Sine alpha plus cosine alpha sine beta. How about cosine alpha plus beta? What is this equal to? Cosine alpha cosine beta. Of course. Do you know how we obtain these formulas? Did anybody show you how this, where do these formulas come up? It comes from them, but they never show it to you, right? So this is how it happens, okay? So you have e to the I theta is equal to cosine theta plus I sine theta, right? You write here e to the I alpha plus beta, okay? So what do you have here? Cosine alpha plus beta plus I sine alpha plus beta, right? On the other hand, this can be written as what? E to the I alpha, e to the I beta, right? What is this equal to? The first part? Can you tell me that? Cosine alpha plus I sine alpha. Second one? Cosine beta plus I sine beta. If you multiply this out, what do you get? Real part, cosine alpha, cosine beta, and I is minus 1, sine alpha, sine beta. And the imaginary part will be what? Cosine alpha, sine beta, right? And the other one is sine alpha, cosine beta. So when are two complex numbers equal? When their real parts are equal and imaginary parts are equal, right? So you have those formulas very easily just popping out of this very nice property, okay? Who understood this? Have you ever seen it done in any other way? Or did anybody show it to you like this? No. So these things are very simple and basic things, but always memorized. So it is wrong. That's why I taught you in the first class Cardano formulas. That's how I started this classroom. You remember? I told you about how to really find solution of second order polynomial. How do you find the roots of it? Not from memorizing formulas, but by thinking. Okay? Here is another example. So mathematics is not a science of memory. It's a science of logic and thinking. So these very complicated formulas, they just become reality very easily like that. Okay, go back to matrices. Okay, now in general, when you have an n by n matrix A, so determinant of A minus lambda I equal to 0 will give you lambda 1, lambda 2, lambda n. You always have n eigenvalues. Some of them could be multiple, but you will always have n. So why is that? Because this is an nth order polynomial. Let's have a look at it. Why is this an nth order polynomial? Okay? So A is A11, right? A12, A1n, A21, A22, A2n, etc. A31, A and N. So A minus lambda I is equal to minus lambda, minus lambda, minus lambda, right? Nothing else changes. And we want to take determinant of this. Okay, I'm being quick because we don't have much time left. So let's expand this. How can we expand this? What was one way of doing it in terms of you could do what? In terms of a column. How can we do this? You just take this is equal to, so let's just expand it with respect to this column. So what do you have? A11 minus lambda times a matrix cofactor of this, right? What is this? A22 minus lambda, A23, A2n, A32, A33 minus lambda, A3n, right? A and n minus lambda. What else? This is one term. What else do we have? A21. Okay, I will do it. It doesn't matter. It will give you the same thing. You are right. A21 times, this will be what? Minus here, right? Minus. So plus, minus, plus, minus. Cofactor. So this is as a matter of fact, if you consider it together with this determinant, we call it cofactor, if you remember. So what is this going to be? So you just erase this out, and what do you have? Cross them out. What do you have? A12, A13, A1n. This is, so this is A32, A3 minus lambda, A3n, A and n minus lambda. Let me write one more. Okay, let me go to the last term here. Okay, minus 1 to the what? This is what are the indices of this? I plus j, right? So minus 1 to the n plus 1 times, what is this going to be? A12, A1n, A22 minus lambda, okay, A2n, and all the way you would have here A and minus 1 n. I want you to make some observations. Why is this? What I'm saying is that this is a polynomial like this. Lambda to the n, okay? Lambda minus 1 to the n, lambda to the n plus some, let's call this an minus 1, lambda to the n minus 1, plus minus 1 to the plus minus 1 to the n minus 1 to the what? Something, okay? It's not, it doesn't matter. I will come back to that. Some A0. So basically it is, well, I'm just going to forget about these minuses, okay? This is some nth order polynomial, okay? I will call this an minus 1 so that we don't get confused. A0, okay? This is a polynomial. What I claim is that this thing is a polynomial of nth order polynomial of in lambda. Can you see that? Of course, I don't expect you to see it in 1 second, but in 5 seconds you should be able to see it. Look at here now. I have here a factor like A11 minus lambda. So none other has a lambda factor multiplying it, right? This starts, one row here is just totally numbers. You have lambda in n minus 2 rows. In all of them, a lambda factor is n minus 2 rows. One of them is just totally numbers, except the one that is coming from the diagonal has this factor. Okay? So how do we continue? What would be the next step after this? I would make an expansion of this with respect to the first row, for example. Then what would I have there? A22 minus lambda, right? And there will be many other terms. But they would again have only one of the rows would have numbers and the others would have A22 minus lambdas, okay? If I continue like this, do you see that in the end, I will have one term that is like this. A11 minus lambda, A22 minus lambda, ANN minus lambda, and lots of other garbage, okay? Lots of other garbage. So nth power, so you see that anything that is coming from the other ones will not have lambda or lambda to the power n minus 1, right? Why? Because there aren't enough lambdas there to multiply. But this, the term that's coming from the leading term will give us this. Okay. What is the power of lambda itself? So it is this times that, right? Always, when you multiply by 2, you will have here how many terms? 4 terms, right? So you will have a number, a term with lambda, and a term with lambda square. Then you multiply it with A33 minus lambda. Then how many terms will you have? 6 terms. So you will have lambda cube, you will have lambda square term, you would have lambda term, and a constant number. So it will continue all the way, and you will always have, so this lambda, what is the coefficient of lambda? How many lambdas do you multiply here? N. So this would be, so AN would be minus 1 to the power n, okay? Let me also do an easy one. This A0, how do I obtain A0? This is very simple. This is the simplest one. Lambda equal to 0. What is that? This is the determinant of A. Right? So this is the determinant of A. This is minus 1. So there is one more. This also we can find from here. So what is this going to be? So lambda to the power n minus 1. How is that going to come out? Can somebody resolve this for me? Okay. What was your name? Can you tell me what will be the power of lambda to the n minus 1? Kindly. It's not written in your telephone. Don't look at your phones in the class, okay? Okay, what would be the power of, what would be the coefficient of lambda to the n minus 1? Very easy, right? Look at this. So only in one term it should miss lambda, right? So you will take A11 from here, right? And in the other ones, you will multiply with lambda. So there will be a term like that, right? So A11 times lambda and the other lambda and the other lambda. So you will have lambda to the n minus 1 times A11. You see that? And there will be another term this time, A22 times lambda and lambda and lambda and lambda. So there will be A22. So what is this going to be? You will have A11 plus A22 plus all the way ANN lambda to the n minus 1. Okay? And what is going to be sign of it? So A11, how many lambdas are multiplied with this A11? So A11 itself is positive. It doesn't have a minus coming with it. So how many of them are multiplied? E to the A minus 1 to the n minus 1, right? As a matter of fact, you could say it like that. Minus lambda to the n minus 1. Isn't it? The rest is not important for me. So I know now 3 coefficients. The leading coefficient is minus 1 to the power n. The coefficient of lambda to the n minus 1 is just summation of the diagonal of the matrix. That's very interesting, right? So there is a polynomial that if you find the roots of that polynomial, they are the eigenvalues of this matrix. And from the beginning, I know the two coefficients of that matrix. So leading coefficient is minus 1 to the n. Okay, if n is 2, it is 1, right? If n is 3, it is minus 1. The second one is just summation of the diagonal, which is called, what is the name for it? Anybody heard it before? Trace. So trace of A is trace of A is A11 plus A22 plus ANN. Okay? So trace of the matrix itself gives you the second coefficient, and the last coefficient is just the determinant of A. Unfortunately, there is no simple formula for the other coefficients. Okay? Of course, when you have a very large matrix, you need special techniques to develop them, to find the thing. Okay, so what are these? Let's look further into that. Okay? Who understood this? Who did not understand it? You did not understand it? Okay. Let me just illustrate it in 3 by 3. Okay? So let's say I have A11, A12, A13, A21, A22, A23, A31, A32, A33. A minus lambda I is equal to, okay, let me write it here. Is it clear so far? Everybody agrees? It's not difficult, so please follow. Do not shy away from it, okay? Do not give up. It's very simple. So I want to calculate the determinant of this. So I will expand this with respect to the first column. So what does this give me? A11 minus lambda times, I'll just erase the column and row that touches that. Okay? So what do I have? Determinant of A22 minus lambda, A23, A32, A33 minus lambda. Then I come here. So the second term is minus A21 times. I erase the row and the column that touches that element. So what do I have here? Please tell me that. A12, A13, A32, A33 minus lambda. And the last term will be A31 times. I touch any row and column that touches that, okay? So I have A12, A13, then A22 minus lambda, and A23. Okay. Everybody following? Who understood this now? Who did not understand it? Please. Back rows. Why didn't you understand this? Any question on this? Please follow. Okay? So, what is this determinant? What is this determinant? A11 minus lambda times. So this is A22 minus lambda, A33 minus lambda, minus A32 times A23. Right? So that is this element. Okay, when you look at here, do I need to continue further? Okay? So I have this and this and this. You see? The term that I talked about, it's there. Okay? It just popped up. Let's look at the rest. Rest just has lambda term, nothing else, right? let's write this one now. Okay, minus A21. So what is the determinant? A12 minus lambda minus and the last one A12 A23 minus A22 minus lambda A13. As you see, this will have lambda cube and lambda square. These will have only lower elements, right? This will also have lambda element. I don't care, but lambda cube and lambda square, meaning lambda to the power n, and lambda to the power n minus 1, will only be A11 minus lambda, A22 minus lambda, A33 minus lambda. Only that will include lambda to the power n and lambda to the power n minus 1. The rest of the terms we have lambda to the minus power n minus 2 and more, okay, or smaller powers of that. Is it now clear? Who understood it? Okay. Where the others get stuck, please ask me. Because this is something really very simple. If you listen to it, you will understand it. Please, where did you get lost? Somebody tell me. You will never have a chance to listen to this again, okay? This is your chance for your life. Please, ask. Okay, I'm not going to insist anymore. Now it's clear that this term is the term that will generate lambda to the power n and lambda to the power n minus 1. And when you look at it, again from here, it's clear that if you multiply now these terms, you will have lambda, lambda, lambda. This will give you minus 1 minus lambda to the power 3, right? And this will give you A11 times lambda, and that times lambda will give you a lambda square term. A22 times this lambda, and that times this lambda will give you lambda minus lambda square. Another one is A3 times this, and that will give you another number. So of course, there will be other lambdas and constant terms also coming from this, right? But we are trying to identify this lambda to the power n and minus 1. The other ones are messy. There is nothing to gain from this. So we are not after that. Okay? So therefore, this is how we obtain this. So this is lambda to the power n. Okay? And this is the trace of the matrix will give you the coefficient of this one. And the zero term is the easiest one. That is just the determinant of it. Then you substitute lambda equal to 0 here. You have A, matrix A back. So determinant of A gives you A0. That's it. Okay. It's not a sequence. It is the trace. It is the trace of the matrix. Meaning, let me just give you an example. Let's talk about this example now, okay? Before I erase it. So we have it here. So he's telling me, okay, why did you tell us this? What's the sense of it, right? I am not finished yet. So now we have A minus lambda I is equal to, we found out, some minus 1 to the n, lambda to the n, plus minus 1 to the n minus 1, and trace of, trace, we write like the trace of A to the lambda to the n minus 1, and you have determinant of A. On the other hand, what is this equal to? If I were to find out lambda 1, lambda 2, lambda n, what would I have? I would have something like this. Lambda 1 minus lambda, lambda 2 minus lambda, lambda n minus lambda, right? So if I were to find n eigenvalues, if I were to know them, I could factor my polynomial into this form, right? Or wrong? Is it wrong or right? If I give you a second order polynomial, if I give, for example, 2 minus x and 2 plus x, this is equal to what? 4 minus x squared. Like it's a second order polynomial. Let's say this is determinant of a minus lambda I, right? So this, if you factor it, if you find the roots, you can write it like this. Okay? These are the roots of the polynomial, lambda and minus lambda. Who understood what is this? Okay. If I give you a polynomial and I ask you what are the lambdas that make this equal to 0, satisfy this. Find the roots of this polynomial. If it is an nth order polynomial, how many roots do you have? N. So lambda 1, lambda 2, lambda n. Then can I write this p lambda like this? Lambda minus lambda 1, lambda minus lambda 2, lambda minus lambda n. Can I write it like that? I can, right? Meaning, for lambda equal to lambda 1, this is 0. For lambda equal to lambda 2, this is 0. For it satisfies, for all roots, this is equal to 0. I could also multiply this out, right? So I could write it in term like this, or I could write it in the factored form. So this is like, if you know the roots of the polynomial, this is how you can write it. Or you can just multiply this out and go back to your original polynomial. You could say that this is an lambda to the an minus 1 lambda to the n minus 1, a1 lambda plus a0. If you multiply this out, you will obtain a polynomial like this. Isn't this better to have it like this here? This is what we are after, right? We are trying to find the lambdas that when we substitute that lambda, this polynomial will be equal to 0. Isn't that the whole game? Yes.
You write it like lambda 1 minus lambda.
Yeah, so what is the difference? Because we have this a minus lambda I, okay? But does it make any difference? I could write this also as lambda I minus a. It doesn't make any difference. Like what matters in the polynomial is there are zeros. As long as you know what you are doing, you take care of the minus and plus accordingly. Okay? Who understood it so far? So far, okay? So far I didn't tell you why am I doing it. So what we will do now is that let's multiply this out. Can you tell me the leading coefficient, lambda n? What is the coefficient of lambda n if you multiply this out? Lambda to the power n. Like you have, how many coefficients do you have? How many factors do you have here? 1, 2, n. So what will be, when you multiply all these factors out, what will be the highest power of lambda? Lambda to the n. And what will be the number in front of it? Because lambda is always with minus, right? Next coefficient. If I have here, so I am looking for lambda to the power, as a matter of fact, minus lambda to the power n minus 1. So what is this going to be? Not there, here, in terms of this one. Okay? What? Not positive. So, see, I have here lambda 1, and if I am looking for lambda, so I will, in one factor, I will take lambda, the constant number, not lambda, and everything else I will take lambdas, right? So this will give me lambda to the power n minus 1. So I will have here, let me write it, lambda 1 plus lambda 2 plus lambda n. Do you agree? You know this for second order equations, right? They say the coefficient of x is summation of the roots which multiplied with minus. And they say the constant term is the multiplication of the roots, right? You remember this from high school. They memorize it. It's very easy to check that. This is what this generalized form. So the coefficients, the roots of the, so what does this tell you? Then plus all the way, and this tells you what? The lot will be the constant term. When you multiply it off, there is nothing with lambda. What will it have? The constant or without lambdas. Somebody, Utku, what is it? Look here. Huh? What will be the term that has no lambda? It's just lambda ones and that's it. So what will that be? It will be lambda 1, lambda 2, lambda 3, lambda n. Just multiply lambda 1, lambda 2. In the other one also don't multiply, don't touch lambda. Just lambda 3, lambda 4, lambda n. Okay? That will give you the term, constant term that didn't touch any lambda. So that will be the constant term. Okay? So what this tells you is that, so determinant of a minus lambda I is equal to minus 1 to the n, lambda to the n plus trace of a to the minus lambda to the n minus 1 plus determinant of a is equal to that. Okay? So what does that tell you? Eigenvalues add up to what? Trace of a. Okay? So whatever they are, lambda 1 to the lambda 2 plus all the way to lambda n is equal to trace of a, and lambda 1 times lambda 2 times lambda n is equal to determinant of a. Okay? For example, in this matrix, I didn't erase it. What are the multiplication of the lambda 1 and lambda 2? What does this tell you? Okay? What is the determinant here? Determinant of A is what? So what is this constant term? Determinant of A is equal to this, right? So this is, these two are equal. Okay? I wrote this here. Okay. So what is the determinant here? 0 times 0 minus 1 times 1, so it is 1. So what was the two eigenvalues here? I and minus I. So if you multiply I and minus I, what do you get? Minus I squared. It's 1. So it checks, right? And what does this tell me? If you add them up, if you add up the eigenvalue, it should give you the trace of the matrix. What is the trace here? 0 and 0. So it is 0. Trace adds up to 0. What is the summation of the eigenvalues? I and minus I, right? Let me give you another one. These are like simple questions for the final, right? I just ask you a very easy question just to help you, and you fail in that one, you are in trouble. So if I were to give you a matrix like this, okay, if I ask you what is this equal to? What is this equal to? So I'm asking you, what does the eigenvalues add to? What is it? Trace, right? Trace of A. So it is 4. And what is the multiplication of two eigenvalues? What is it? Is it 3? It is the determinant. 3 minus 2. This is 5. Okay? So if I ask you, if I can give you, of course, a 10th order matrix, okay? I can give you a 10 by 10 matrix. And if you start to solve the 10 eigenvalues so that you can add them up, and you can multiply them and give me the answer, even if I give you 10 hours, it will not be enough, right? So therefore, it is very important that you think before you start working. Okay? So Ahmed, how much more hint I can give them? Okay. So this is trace and determinant are related to the eigenvalues in this very nice and simple manner. Okay. Diagonalization of matrices. Now let's say I have a matrix, n by n matrix A, and I have lambda 1, x1, lambda 2, x2, lambda n, xn, meaning ax1 is equal to lambda 1 x1, ax2 is equal to lambda 2 x2, xn is equal to lambda n xn. Okay? Let me do the following. All these have something in common. What is that? It's A that connects them together, right? I will do the following. These are vectors, isn't it? Can I stack them in a matrix and say the following? I want to have ax1, this is the one column, ax2, axn. So this is the first column, second column, nth column. These are columns, right? And what is this equal to on the other hand? So the first one was equal to lambda 1 x1. Second one, lambda 2 x2, lambda n xn. So this is another way of writing the same thing. There is no difference here, right? Now, this, I can write it as follows. x1, x2, xn. And here, I want to have a diagonal matrix. If I multiply this, I get this. Let's check it, okay? So what is this? This, when you multiply with this, what does this do? This multiplies the first column, lambda 1 multiplies the first column, lambda 2 multiplies the second column, lambda n multiplies the nth column, right? Therefore, this and these are equal. Does everybody agree? Who did not understand this? Please raise your hand. This is just matrix multiplication. These are vectors. Okay, these are numbers. So this means exactly this. So if you multiply this out, this is what you get. Okay? Let's now have a look here. Since A is common in all these vectors, let me take A out here. So I have an n by n matrix, and I have these vectors. Now this becomes what? A matrix with n column vectors, isn't it? So this, again, is like, I can call this matrix X. What is this? This is also matrix X, isn't it? So I can say the following in that case, can't I? AX is equal to X, and let me call this big lambda, okay, capital lambda. In Greek, this is called capital lambda, okay? X lambda. Okay? This is, we didn't do anything here, right? We just solved for eigenvalues of A, and we obtained the corresponding eigenvectors, and we just stuck the eigenvectors together in a matrix, and we called it X. Now, if this X has linearly independent columns, okay? We assume that, right? We assume that x1, x2, xn. So we have n linearly independent eigenvectors. When do you have it? When you don't have it, we will talk about that, okay? I discussed it an hour ago, but there are some special cases that it is guaranteed, and there are other cases it is not guaranteed, okay? But let's assume they exist. In that case, can I write the following? If x is non-singular, then what do I have? Let me multiply with x inverse from here. X double, this is 1. Of course, more important one is what? You multiply with x inverse from here. X inverse AX okay? So these eigenvectors are very special vectors. If you just put them in a matrix and form an X, and you make this kind of a transformation on a matrix, inverse of that matrix times A and matrix itself, it will be diagonal. Let's just continue with that example, for example, here. So this matrix A is equal to this. So lambda 1 was I. Lambda 2 was minus I. What was x1? The eigenvector, what was it? Was it I1 or minus I1? Can you please check? Minus I. Okay, good. And for this one, right? So what this is telling us is the following. Form a matrix with x1 and x2, which is minus I1 and I1, okay? X inverse will be what in this case? What is it going to be? Inverse of it. So let's calculate the determinant. What is the determinant? A times B. So minus I. Minus C times D. So minus I. Minus I. So minus 1 over minus 2I times. What happens to these? They will exchange, right? And these will change sign. So you exchange these two, you change the sign of those. So this becomes, if I comes up here, okay, you multiply it with I and I, this will be, so this will be I over 2. So this is going to be, whatever, it doesn't matter. So I can keep it like that, okay? So what is this telling me? X minus AX. So minus, so I over 2, 1 minus I, minus 1 minus I, times I, which is 0, 1, minus 1, 0, times X, minus I, 1, 1, should be equal to I, 0, 0, minus I. Is this true? What is this telling me? Okay, without getting into those things, let's just do the calculation. Okay? This? You multiply both numerator and denominator by I, okay? That's why I did those complex numbers. So you multiply with I and I, upstairs and downstairs. So you have minus 2I square is minus 1, so it becomes plus, and you have I there, okay? Okay, so this is going to give you I over 2 times this is, what do you have here? 1 times 0, I. This gives you 1, and this gives you I. And this minus 1 times minus I, 1, 1. So what is this equal to? This times that. So I, this is I times I, so minus 1 plus 1. Okay, plus 1. And this is, I make a mistake there. I square minus I square plus 1. And yes, this gives you what? I, so equal I square minus 1 and I square. This gives you minus I square minus 1, and this gives you I square minus 1. See, when complex number come into the picture, you need to switch back and forth. Okay? So this is, of course, there is also here I over 2. I over 2. Okay, so what is minus I square? It is plus 1. And one more is 2. So you have here then, so this is 2. This is I square minus 1 is, this is minus 2. Is that minus 2? It should be 0. I square plus 1. It's plus 1. See? I square plus 1, right? So it should be 0, okay? Okay, this is plus 1 minus 1, that is 0. And this is minus 1 minus 1, that is minus 2 times I over 2. So what is that? That is, if you multiply 2 will cancel. This is I, this is 0, this is 0, and that is minus I. So did we get it? Yes, right? So this is called a similarity transformation. Of course, in general, similarity transformation is this. I give you a matrix A, and I give you a matrix T. T inverse AT is called a similarity transformation. Okay? Let me give a 5-minute break. Everybody is very tired. Nobody is participating. Okay? Okay. Now, if you know a set of eigenvalues and eigenvectors, then you have A x1 xn is equal to in other words, you call this x, you call this capital lambda ax is equal to x lambda. In other words, A is equal to x inverse. Or conversely, x inverse Ax is equal to gamma. We call this diagonalization of matrices. So let me ask you a logical question. When can you diagonalize a matrix? What would you think? I'm not asking you to prove it, but what is your impression? When can you diagonalize a matrix? No. That's not the answer. It has to be single, of course. We are talking about, when we are talking about eigenvalues, we talk about square matrices. If it has a set of n linearly independent eigenvectors, right? It doesn't matter whether eigenvalues are distinct or not, but if for that given matrix A, you have n linearly independent eigenvectors, then you can diagonalize it. Okay, that is the most general fact. Okay, what is the use of it? Now, let me calculate a square. Okay, let's calculate a square. What is it from here? A is equal to x lambda x inverse, right? So if I multiply it by itself, x, so remove this parenthesis, okay? This gives you identity, isn't it? So what do you have? X lambda times lambda, lambda square, x inverse. How about if I calculate a to the n? What will this be? Huh? X. What does it tell you about the eigenvalues of a to the power n and eigenvectors of a to the power n? So if I were to ask you, okay, a has like here, okay? Then what are the eigenvalues and eigenvectors of a to the power 11? What are you going to do? Are you going to start multiplying a 11 times and try to find then eigenvalues and eigenvectors for me? If you do that, what's going to happen? You'll just spend entire exam time, right? So that's why when you feel that, oh, too much time is needed, what the hell, what's this question? You should immediately think that doctor would not ask such a question, okay? I am missing something here. Leave that question, go to another question, and come back fresh and think about it again. Try another way, okay? I would never give you something that would require you to do endless amount of computation. There is no such thing. That's not mathematics. You are not calculators. You are engineers, okay? So therefore, so what would that be? What would be the eigenvalues? They are lambda I power 11. And what are the eigenvectors? What are the eigenvectors? Who's going to tell me? What are the eigenvectors? Just x, no change, right? So xi. So eigenvectors remain the same. This is what it tells me. Okay, why? Why is that? Just multiply. So a to the power n, x is equal to x. That's it. Isn't so? When you have such a thing, doesn't that mean that these are just the columns of these are just eigenvectors? That's it. Of course, we could see it another way. Okay, I have a times xi is equal to lambda I xi. Okay, I multiply with a again here. What do I have? A square xi lambda I times a times xi, right? I'm just multiplying the entirety left and right. I multiply with a. So what do I get here from here? A times xi is so lambda I times lambda I xi, which means lambda I square xi. If I multiply with a again, what am I going to have? So what we observe from here can be seen also from the definition of eigenvalues and eigenvectors, isn't it? So you remember when we solved the difference equation last week, what did we get? We said, if you remember, in multivariable case, when you have xn plus 1 is equal to a times xn, and x0 is just this difference equation, if you remember. We talked about how to obtain a solution of this, and what did we find out? You remember? We look for a solution like this, right? We said, how about we look for a solution like this, lambda to the n, c. And we found out that this lambda NC exactly has to satisfy this. Who remembers this? Okay. Okay. So therefore, when is this stable? Another concept, right? Stability. Meaning, if you turn on a system, okay, you don't give it any input. You just leave it by itself. You just turn it on. It could be a machine. It could be an airplane. It could be just any electrical system. You turn it on. If it just starts growing and making noise and it starts oscillating and destroy itself, it's called unstable, okay? And if you don't give any input, if it just dies down and starts waiting for you to do something, to give it something so that it can process it, it's called stable. If a system by itself generates unbounded outputs, it's called unstable, okay? In signals and systems and automatic control courses, we are going to teach you this formally in details. But as far as today is concerned, if a system with just initial conditions starts giving out unbounded outputs, it's called an unstable system, okay? So when would this be unbounded? Lambda to the n, when n grows, like it becomes like, when, for example, lambda is 2. So how will this grow? If you look at it in the time scale, okay? So for n equal to 1, this is going to be 2, right? For n equal to 2, this is going to be 4. For n equal to 3, 8. So it will keep growing, explode. With just initial conditions, such a system would give larger and larger and larger outputs. What do we call these? These are called unstable systems. When would this be stable? When would such a thing would not happen? Meaning, when n grows, instead of going to infinity, what would I like it to happen? Go to 0, right? It becomes smaller and smaller, so and smaller, because I'm not giving it any input other than the initial condition, okay? So if lambda was, for example, 0.5, so what is square of, for n equal to 2, what is it? 0.25. For n equal to 3, it is 0.125. For 4, it could be 0.0 something something. After 5, 6, 7, it would be 0.0000 something, right? It would be practically 0. It will die down. It will be stable. So we say that if lambda I, absolute value of lambda I less than 1 in discrete time case, in difference equations, and the system is stable. Otherwise, it is unstable. Of course, here you don't have to know their exact value for stability. What do you need to know? If their absolute value is less than 1, okay? There is a big difference between the two, okay? For continuous time systems, what was it? X dot is equal to AX. And X0 was, we gave you something. And what did we say? Let's guess a solution like this. E to the lambda t C. And we again arrived at the same question. This has to be satisfied, right? So when will this be stable? Meaning when, in continuous time case, when t goes to infinity, if you don't have any input, just from the internal initial energy, system should not give you larger and larger and larger outputs. It should die down, right? We call such system a stable system. If otherwise, if it just by itself, without pumping in anything new, any input, if the response of the system is growing all the time, we call that unstable. So when would that happen for lambda? For how are the, let's plot this e to the t here. E to the lambda t, okay? So e to the lambda, let's say lambda is positive. How would that be? For lambda, t equal to 0, this is t, okay? This is, let's say, ft. For t equal to 0, it is 1, right? When t grows, e to e squared, e cubed, e 100, what happens? It's just exponentially it grows, right? When t is negative, what happens? If you go to 0, like this. So e to the t, e to the lambda t, for lambda greater than 0, will be like this, something like this, right? When lambda is negative, what happens? How will this plot change? It will be the other way around, right? It will be, again, for t equal to 0, it is 1. And when t grows, it will approach to 0, okay? So such systems are called stable systems, meaning is when you have just initial conditions and you find the solution of the differential equation, the x of t's, any one of them, should just die down. Okay, that happens when lambda is less than 0. As a matter of fact, considering that lambda could be complex, how should that be? It's not true because you could have also complex eigenvalues, right? We should say, instead of saying lambda is less than 0, we should say real part, imaginary part. Okay, so that's why we went over it. So if I have lambda, let's say, is equal to -2 plus I5, okay? Lambda 1 and lambda 2, of course, you have to have complex conjugate of that. Any polynomial with real coefficients will always have real roots or complex conjugate roots. So you cannot, if you have a complex root, you will always have that its conjugate is also a root, okay? Because it has real coefficient. So when you have such a factor, well, what would this happen? Lambda t would be what? E to the -2 plus I5 t, right? So let me separate this e to the -2t, e to the I5t. So this is e to the -t times, this is what? Cosine 5t plus I sine 5t. What happens to this when t changes? This factor, cosine t, cosine 5t. What is the largest value cosine 5t can take? 1. What is the smallest? -1. So it's just between -1, same thing for sine, right? So this complex number is just oscillates between -1 and +1 and -i and +i. So it is bounded, right? This one, when t grows, what happens to this one? It goes to 0 when t grows, right? Don't be afraid, just speak up. It goes to 0. So therefore, what is this -2 here? It is the real part of the eigenvalue, isn't it? So the condition is, so instead of, so here we said absolute value, right? Where was it? Where was, where did I do? Did I erase it? No, it's here. I said absolute value, so I'm okay here. Absolute value for complex number, right? It should be inside the circle. So here I should say real part of lambda should be less than 0. And real part of lambda should be greater than 0 for stability. So this is really control theory, and system theory is entirely based on this. Everything we do in system, and my PhD was on control theory. Everything we do, the first requirement is that the system you design, it has to be stable. If it's not stable, you cannot talk about other performances of it, right? So it has to be a stable system. After that, you start talking about having optimal performance and this and that and whatever. So stability is the most basic thing that you have to require, and that requires that the closed loop matrix of the system, this A, has to have all of the eigenvalues having the real part of the eigenvalues less than 0. Or if it is a discrete time system, absolute value of the eigenvalues should be less than 1. Okay. Now, we talked about eigenvalues, eigenvectors. I want to prove to you now that if you have distinct eigenvalues, the eigenvectors will be linearly independent. Okay? So let's do this. We are a bit tired, but should we do this? Can you pay attention? I think it's good to go over this. Okay? And I have a bad habit of asking proofs in the exams, as you know. But I don't want you to memorize the proofs. I want you to understand it. Therefore, you are welcome to ask as many times as you require to make sure you understand it. Okay. Theorem. Given n by n matrix A, if A has n distinct eigenvalues, then its corresponding eigenvectors are linearly independent. This is very important, isn't it? What this is telling you is that if you have n distinct eigenvalues, you can diagonalize that matrix. It's very, very nice property. So how do we prove this? Okay, what does this mean? This means I have ax1 is equal to lambda 1 x1, ax2 is equal to lambda 2 x2, axn equal to lambda n xn. And lambda 1, lambda 2, lambda n, they are all different from each other. None two are equal, okay? So we will just prove this by contradiction, okay? We will say that proof. Assume otherwise. Meaning, let's say lambda 1, lambda 2, lambda n are distinct, but x1, x2, xn is not a linearly independent set of vectors. Okay? Is this clear? So we want to prove it by proof by contradiction. We are saying that, okay, assume that lambdas are distinct and we have x1, x2, xn, but assume that they are linearly dependent. What would that mean? set of n vectors are linearly dependent would mean what? What is the definition of linear independence? You remember that? If I give you n vectors. Huh?
You can get one of the vectors by linear addition.
Yes. You can, that would mean, like Hussein said, that would imply that for at least one lambda I, let's say it is, let's rename them, let's call it lambda 1, okay? If it's not lambda 1, we can reorder them, you can rename them and call it lambda 1, right? There is no natural order of lambdas. So let's say lambda 1, okay? If it's not lambda 1, let's rename them and call that lambda 1. Is it okay with you? Let's say lambda, let's call it lambda 1. It would mean, okay, then it would imply that lambda 1 can, I am writing it lambda 1 so that you can have easy time to understand it. Lambda 1 can be written as linear combination of other eigenvectors, which mean x2, x3, xn, right? See? You agree? x1 can be written as alpha 2, x2 plus alpha 3, x3, alpha plus alpha n, xn. Right, Husni? That's what it would mean. That's what you said. So you can write, if x1, x2, xn are linearly dependent, that means you can write at least one of them as linear combination of the others, right? That's what it would mean. And I call that one as x1. Okay, what would I do now? What would be the logical thing to do? These x1, x2, xn, they are eigenvectors. So when does that help me? When I hit this with A, right? So I just A times that, okay? So what do I get? A times x1 is equal to A times alpha 2 x2, alpha 3 x3, alpha n xn. What is this? Ax1, lambda 1, x1. What is this? A alpha 2 A x2, alpha 3 A x3, alpha n A xn. So what is Ax2? Lambda 2 x2, lambda 3 x3, lambda n xn. Let me divide this by lambda 1 so that I have another expression for this. Okay, divide by x1, lambda 1 both sides. So what do I have? x1 is equal to alpha 2, lambda 2 over lambda 1, x2, alpha 3, lambda 3 over lambda 1, x3, alpha n, lambda n over lambda 1, xn. So let me subtract this from that. Okay? So what do I get? 0 is equal to what? Alpha 2, 1 minus lambda 2 over lambda 1, x2. Are you following? Are you following? Is it okay so far? Who understood so far what I am doing? Good. The others will also very soon understand. So what I did is very simple. We said that, okay, there is nothing magical here. We said that we have alpha 1, alpha 2, alpha n, they are all distinct, meaning none of the two are equal. They are all different numbers, okay? There are no two numbers repeated. Eigenvalues are all different. We call them distinct eigenvalues. And I have, of course, when you have a distinct eigenvalue, null space always has dimension 1, right? Because the determinant is equal to 0. Therefore, we are okay to say that for every eigenvalue, I will have an eigenvector. Is that true? Because null space determinant of A minus lambda I times I will be equal to 0. Therefore, that means null space has at least dimension 1. Do we agree? So therefore, we have n eigenvectors. For every eigenvalue, we will have an eigenvector. Do we agree so far? Okay? Do we agree on that one? Good. So we say, what we are saying is that theorem is saying that these eigenvectors, since they are eigenvectors of distinct eigenvalues, they are linearly independent. So this is what we are trying to prove. So how do you prove such a thing? We said that let's assume otherwise, meaning let's assume that, yes, eigenvalues are distinct, but eigenvectors, this set of these n eigenvectors, they are linearly dependent. So linearly dependent means what? It means you can write one of these n vectors as linear combination of the others, right? That's what it means. Okay, so that's what we said. We said that let's assume that that vector, there is such a vector, and we just renamed or we numbered as x1, just so that I don't have to use xi and xj's and confuse you, okay? To make the proof simpler, without losing generality, I said let me call that vector, which can be written as linear combination of the other vectors, let's call it x1. Okay, we said, here it is. So you can write this x1 as linear combination of other vectors if they are linearly dependent, right? So we said, let's multiply this x1 with a in both sides. Okay? So you have here ax1. In the other side, you will have a times this parenthesis. Since they are equal, after multiplication, they will still be equal, right? So left-hand side will be lambda x1. And right-hand side, since you have a matrix multiplying addition of other matrices, you have the distribution law, right? So you can just make it first, instead of first adding, then you can first multiply and then add. No problem. So ax2, and you end up with this, since these are all eigenvectors, that's the definition of x's. So you have ax2 is lambda 2x2, lambda 3x3, lambda 10xn. So you end up with lambda 1 x1 is equal to this. And you divide by lambda 1, assume lambda 1 is not 0, okay? Assume lambda 1 is not 0. If it is 0, we will deal with otherwise, okay? Assume lambda 1 is not 0. So you divide by it. What do you have? You have this expression. So you have x1 is equal to this in terms of a linear combination of x2, x3, xn. And you have another linear combination of x2, x3, xn. Okay? So let's subtract them. So we are subtracting this without a and with from this. So you have alpha 2, lambda 2. So alpha 2 is common in both of them. Here you have 1, you have lambda 2 over lambda 1 times x2 plus alpha 3, 1 minus lambda 3 over lambda 1, x3, all the way alpha n, 1 minus lambda n over lambda 1, xn. Okay? When could this be satisfied? There are two cases, right? What are these? If lambda 1 is equal to lambda 2, but we said they are not. We said they are distinct. So that cannot happen. Okay? So none of these are all different from 0, right? Why? Because they're distinct. Because the eigenvalues are distinct. Because the eigenvalues are distinct. Because they are distinct. Okay, in that case, what does it mean? You have what? A linear combination of x2, x3, xn is 0. What does that mean? They are linearly dependent, right? So you will go all the way like this. Can you see that in the next step we will do the same thing? Okay, we will say that assume you can write x2 in terms of x3, xn, right? And we will do the subtraction, and we find out that x3, x4, xn are linearly dependent, right? In the end, what are we going to come to? We'll come to 2 vectors, right? So let's see, in the end, so last step like this, okay? This assumption takes us all the way now to the last step. Who understood this so far? You didn't understand it? Where did you get stuck? Please tell me, ask me. Okay. So after n minus 1 times we continue like this, okay? We will end up here. We will find out that 0 is equal to some alpha 1 bar xn minus 1 plus, let's call it beta, okay, beta 1, beta 2, xn. This is going to be after so many steps. Every time we will eliminate one other vector, we will go all the way and we will arrive at this one. So, what does this tell me? This tells me that this one vector can be written in terms as a multiple of the other vector. Okay, let's see if that's possible. Okay, so you multiply with a. So what do you get? 0 is equal to. So this is beta 1 a xn minus 1 plus beta 2 xn, right? So it's beta 1 a xn minus 1 beta 2 a xn, which will be beta 1 lambda n minus 1 xn minus 1 plus beta 2 lambda n xn. Okay, solve for xn from here and substitute in here. Okay, x or xn minus 1 is equal to minus beta 2 over beta 1 xn. You substitute in here, what do you get? 0 is equal to beta 1 lambda n minus 1 beta 2 over beta 1 xn plus beta 2 lambda n xn equal to 0. So this beta 1 goes away. What do you have? 0 is equal to lambda n minus 1. I'm sorry, this is minus right here, minus. Minus lambda n minus lambda n minus 1 beta 2 xn equal to 0. So what does this tell you? Lambda n has to be equal to lambda n minus 1. Right? Which may not happen. So therefore, it is not possible. We showed from all the steps that as long as lambdas are distinct, there is no way to satisfy this. Okay? There is no way to satisfy this linear dependence condition as long as lambdas are dependent. Okay? Let's continue next class. I will also touch upon this, and I will start talking about symmetric matrices. It's very, very important. That is the climax of this course. Okay? So I will see you next week.